Okay, hello everyone. Let's get started. In the last lecture, essentially we looked at a simple algorithm, right, on a collocated grid. Essentially, how to solve it. The complete algorithm we have kind of listed it. Now, in today's lecture, we're going to solve a problem using simple algorithm on a collocated grid. Okay, so essentially we will first set up the problem, and then we will see how to code this and try to run it. Okay, so that is the agenda for today. So we will take the same problem that is there in the Patankar's book, which was kind of we have already done this for a staggered grid. Okay, so we are now reformulating a problem statement such that we can apply it for a collocated grid. All right, so let us consider the one-dimensional flow through a porous medium governed by C mod u plus dpdx equals 0, where C is a constant. This is the constant that it's kind of represents the porosity of the medium, and the continuity equation is given by partial x ua equals 0. Okay, ddx ua equals 0. So we are given both the equations, and then now we have unlike the staggered grid, we have the collocated grid where we have two cells, that is the cell B and cell C, where the velocities and the pressures are stored here. Okay, so UB, PB and UC, PC are all stored at the cell centroids of these cells. Okay, now in addition we have three faces, that is 1, 2, 3 here, which are basically west and east faces for B cell, and 2 and 3 form the west and east face for the C cell. Okay, now so on these faces we also would need the velocities, that is u1, u2 and u3, which would be utilized in writing the continuity equation for cell C and cell B. Okay, so we would also need to keep track of these velocities, and we would also need pressures on the faces, that is P1, P2, P3, which would be required when we write the adjacent pressures for these equations. Okay, so I am kind of denoting the faces using 1, 2, 3, and the respective variables are u1, p1, u2, p2 and u3, p3. Okay, now the other problems that are given, other variables that are given in the problem are the grid spacing, that is x2 minus x1 equals x3 minus x2 equals delta x is 2, that is given, and the cross sectional areas at the faces, that is a1 is 6, a2 is 4 and a3 is 2, that is what is given. Of course, the value of C at all the locations, C1 equals C sub 1 equals C sub 2 and so on, all the C's can be taken to be also constant. Okay, and also it can be even at some CB and so on. Okay, so this can be taken to be constant. Then the boundary conditions are given, that is the velocity at the phase 1 is given as 10 units per second, and on 3 is given as u3 equals 30 meters per second. Okay, now what we see is that both the boundary conditions that are given are for velocities. Okay, so essentially there is no boundary condition for pressure that is given in this problem. Okay, now the question says you calculate the cell velocities and the cell pressures, that means UB, PB and UC, PC, and as well as we were asked to calculate what is the boundary pressures P1 and P3, because these were not given, only the velocities are given as boundary conditions to calculate what will be the boundary pressures. Okay, now it also tells us take an initial guess of UB star equals UC star equals 15. So essentially these are the star values, UB star equals UC star equals 15. Okay, and then it also gives you the pressure guess. These are also the star values, PB star, PC star, P1 star, P3 star can be taken as 120. Okay, so that is given in the problem statement. Okay, the initial guess is given. All right, let us look at the solution using a simple algorithm on a collocated grid. Okay, so essentially the first starting point is basically we have to first integrate the momentum equations on cells B and C. Okay, so that means discretize the momentum equation on cell B. Okay, so that is the first step. So that means we have C mod u dx plus dpdx equals 0. Cell B has faces as 1 and 2, right? If you look at here, cell B has 1 to 2. So that means 1 to 2, integral 1 to 2, C mod u dx plus integral 1 to 2 dpdx dx equals 0. Okay, so this as you know, we are treating it as this basically is a source term, right? It doesn't belong anywhere else. So that means C mod u delta x would be evaluated the cell centroid, that is B, that is CB mod UB delta x. We would consider this as AB. Okay, so AB times UB plus integration of this quantity would give you pressure. That means P2 minus P1 equals 0. Okay, so if you write this equation with considering AB as CB mod UB delta X, then the momentum equation, the discrete momentum equation for cell B is ABUB equals P1 minus P2. Okay, let's call this equation number 1. Now we have to, of course, underrelax this equation. So if you underrelax this equation, what you get is basically divide by alpha here and add the respective quantity on the right hand side. That would be AB by alpha UUB equals P1 minus P2, plus you have to add this extra quantity on the right hand side, that is 1 minus alpha U by alpha U times ABUB star. Okay, so that means if you redefine your new AB as AB by alpha U, then I can still write this as ABUB, where I would just say I divide by alpha U for my AB and again update its value. Okay, that means that is my new AB. So ABUB equals P1 minus P2 plus, this term basically is known quantity, it would be called as B sub B. Okay, so this is ABUB equals P1 minus P2 plus B sub B, and that is your equation 2. Okay, which is basically the underrelaxed form of equation 1. Okay, that is equation 2. Alright, so this is the discrete equation. In after under relaxation for cell B. Okay. Alright. Of course, the problem statement is such that we don't have any other dependence on the neighboring cells, right? The only dependency is on the cell itself and on the pressures. There is no neighboring cell that is coming into play here. Okay. Now let us see. Let us go and discretize the momentum equation for the other cell, that is for the C cell. Okay, so discretize momentum equation for cell C. That's your phases are now 2 to 3 C mod u dx plus integral 2 to 3 dp dx equals 0. So again, the cell centroid value of this would be C, that is C sub C mod uc delta x times uc plus integration of this is pressure, that will be P3 minus P2 equals 0. Okay. So if you denote again this coefficient Cc mod uc delta x as AC, then what we have is AC uc equals P2 minus P3 on the right hand side. Okay, so this is, let's call this as equation 3, which is the discrete momentum equation for cell C. Of course, because of the nonlinearity in the source term, we have to also underrelax this thing. So the underrelaxed equation for equation 3 is basically AC by alpha u uc equals P2 minus P3 plus 1 minus alpha u by alpha u times AC times UC star. Okay, so again this quantity can be considered as some B term, that is B sub C, and this is your pressure term, that is P2 minus P3. On the left hand side, if you denote AC by alpha u as again as an AC, then we can write this as A sub C U sub C equals P2 minus P3 plus BC. Okay, so that's what we have. All right, that means this is the discrete momentum equation, right? That is also underrelaxed, right? For cell C, right? Okay. So we have these equations, equation 2 and 4 for cell B and cell C. Okay. Now, one more thing that we have to do different from what we have done in the staggered mesh case is that the boundary conditions U1 and U3 are given, right? But we don't know the pressures for these locations. P1 and P3 are not known, but in order to know them, we need relevant equations, right? So the equations are basically the same governing equation. It is just that the same governing equations control how pressure and velocity are related. So in order to do this, in order to know the value of the pressures, instead of making an approximation, what we do is we take an approach where we discretize the governing equation on this kind of a half cell. Okay, so let me take a half cell with a centroid assumed to be at 1. So we have a half cell that's kind of like this. You can see here that I am not taking the centroid to be at the cell center. Okay, so essentially I am taking the cell is like this, and 1 happens to be its representative value. Okay, in order to derive an equation for pressures and velocities on the boundaries, okay, which would be needed to update the pressures. So if I consider a control volume that is like this, so then I can go from 1 to B C mod u dx plus integral 1 to p dp dx equals 0. This is basically your integration of the momentum equation for some kind of an half cell with 1 as its representative value. Okay, so that means then we can write this as C1 mod U1 times integral dx would give you delta x by 2, because now this is only over a range of delta x by 2 times U1 plus we have PB minus P1 equals 0. Okay, so this is basically going to give you, if you call this as some coefficient A1, what you get is A1 U1 equals P1 minus PB, right? Now P1 and PB of course are not equal, right? Because essentially you have C mod U dx, that is the this porosity is going to have a pressure drop from P1 to PB. That is why we are now deriving this equation, right? How the velocities and the pressures are related within this half control volume, such that this pressure can be computed accordingly, right? So that's why we have done this thing. Okay, all right, so that means we got an equation. This is basically discrete momentum equation that is written for the boundary half cell that is for centered at 1. Okay, let's call this equation 5. So similar to what we have done for B cell and C cell, here also we would do the under relaxation. So if you under relax cell 5, what you basically, equation 5, what you get is A1 by alpha U times, this is incorrect, this is supposed to be U1, isn't it? It's supposed to be U1 equals, so this is basically U1, okay, this is not correct, it's supposed to be U1, okay, equals P1 minus PB plus 1 minus alpha U by alpha U times A1 U1 star is what we have. Okay, let's call this again as some A sub 1, this coefficient A1 by alpha U. Then this would basically become B1, right? Then we have an under relaxed equation that is basically A1 U1 equals P1 minus PB plus B1. Okay, so equation 6 is basically under relaxed discrete equation, momentum equation for some kind of a half boundary cell, which we want to have, because in order to apply boundary conditions and in order to get the value of the pressure P1 on the boundary, we would need this equation. Okay, now similarly we will also discretize the half cell that we would get on the other side, that is at the vertex 3, right, on phase 3. So basically this would be, if you consider a half cell that is extending from C to 3, right, we will again integrate the momentum equation in order to get the pressure relation between P3 and PC. So this will be integral C to 3 C mod U dx plus integral C to 3 dp dx equals 0. Okay, so what we have is basically C3, again if you consider that for this cell 3 is kind of a representative of the centroid, then what we have is C3 mod U3 delta x by 2 times U3 plus we have P3 minus PC equals 0. Okay, so again if you call this coefficient as some A3, what we have is A3 U3 equals PC minus P3. Okay, so equation 7 is basically your discrete momentum equation for the half cell that is written about phase 3, right? Okay, now we will also under relax this equation. This is basically gives you A3 by alpha U times U3 equals PC minus P3 plus we have on the right hand side 1 minus alpha U by alpha U times A3 U3 star. Okay, so let us again call this A3 by alpha U as A3 itself. Okay, essentially you divide and then store it in the same variable. Then we have A3 U3 equals PC minus P3 plus this entire term would be called B3. Okay, so now equation 8 is your discrete momentum equation written for the half cell that is basically centered or about phase 3, right? Okay, so now equations 8 and 6 that we have derived before, these two equations now relate the boundary pressures to the cell pressures with the boundary velocities. Okay, that means we got a relation between the boundary pressure and the cell pressure, adjacent cell pressure, in relation to the boundary velocity. These are required in order to update the phase pressures from the velocities, phase velocities that are given, and the cell pressure that we would calculate. Okay, so that is the significance of writing this kind of a half cell thing, which was of course not there in the staggered mesh case, right? Because you already had because the pressures and the velocities are anyway staggered, so you never had to do such a thing before. Okay, all right. Now Okay, so let us now move on with the algorithm. So essentially, once you have written the discrete momentum equations, you can solve for them. You can also calculate the hat velocities. Okay, so we go back and list out all the four equations that we have for the cells. This is for essentially for momentum equation for cell B, and this is for cell C, right? And this is for node 1, and this is for node 3, right? What we had was ABUB equals P1 minus P3 plus B sub B, and ACUC equals P2 minus P3 plus BC. Similarly, we had for nodes 1 and 3 as A1 U1 equals P1 minus PB plus B1, and A3 U3 equals PC minus P3 plus B3, right? So this is what we have. These are the four equations that we have derived. Now we can of course write these in UB hat notation by dividing with AB, right, on the right hand side. That means I can write this as UB equals UB hat plus some dB times P1 minus P3. That means where UB hat is your BB upon AB, right, B sub B upon A sub B, that is your UB hat, plus your dB would be 1 upon AB, that is multiplying P1 minus P3. So dB would be 1 upon AB, right? Now similarly we can write a equation for cell velocity UC in terms of hats as divide everything with AC, then what you have is UC equals UC hat plus some DC times P2 minus P3, that is your UC equals UC hat plus DC times P2 minus P3, where your UC hat is your BC upon AC, right, and your DC value is your 1 upon AC, right? That's what we have. Okay, we have basically just divided with the central coefficient on the both sides. So that is how we got these hat velocities and the coefficients d that multiply the pressure differences. Okay, that is clear. Now we of course would also like to write these two also in terms of hat velocities. Then you divide this entire equation with A1. Then what you would get is you would get an equation U1 equals U1 hat plus D1 times P1 minus PB, where U1 hat is B1 by A1, that's B1 by A1, and D1 would be 1 by A1, right? Okay, similarly we would also like to write a corresponding equation in terms of hat for node 3 as well. So this will basically give you, if you divide everything with A3, you will get U3 equals U3 hat plus D3 times PC minus P3. So where your U3 hat is B3 upon A3 and D3 would be 1 upon A3, right? So again we just converted the four discrete momentum equations excuse me, into this kind of hat form. Okay, now what is the main step? The main step in simple algorithm on collocated grids is basically use momentum interpolation and calculate the phase velocities, right? So we have two cells B and C. The only phase that we have is 2, right? The other two phases that are on the boundaries 1 and 3 are not very much interesting as such, because the velocities there are already given. U1 and U3 are given, so we don't have to use as such a momentum interpolation there to obtain the velocity there. So we will use momentum interpolation and obtain the phase velocity U2. So what do? Using momentum interpolation, you can write the phase velocity U2, that is U sub 2 equals U2 hat plus D2 times the adjacent pressures. For phase 2, the adjacent pressures are B and C, right? So that means U2 equals U2 hat plus D2 times PB minus PC, right? That is, let's call this equation 9, where U2 hat would be, you would obtain it as arithmetic average of UB hat and UC hat, and D2 you would obtain as arithmetic average of DB and DC, right? This is basically the simple algorithm on collocated grid, right? So this is the main assumption that we have made. Obtain the phase velocities by through momentum interpolation, that is through the hat velocity and the adjacent pressures. Okay, all right, so this is clear. Now once you have the momentum interpolated phase velocities, we can go and discretize the continuity equation. Now where do you discretize the continuity equation? In the context of staggered meshes, we were discretizing the continuity equation on the pressure cell, right? Now in the context of collocated meshes, you will discretize both the momentum equations and the continuity equations always on the single cell, that is basically the primary cell, which are basically cell B and cell C, because you don't have any other cell to discretize, right? Okay, so discretize continuity equation on cell B, That basically gives you integral 1 to 2 d by dx ua equals 0. So this is going to give you u times a evaluated 2 minus 1. Okay, that's u2 a2 minus u1 a1 equals 0. So if I write this as, if I split this again into prime and star values, what you get is u2 prime a2 plus u2 star a2 minus u1 is already u sub 1 is known, right? This is basically given boundary condition. So you cannot split u1 into u star and u prime. You would leave it as it is. This is u1 a1 equals 0. Okay. So from here we are interested in, of course, obtaining a pressure correction equation eventually. So what we do is we leave u2 prime a2 on the left hand side and send everything else to the right hand side that is known, right? So what is known here? u1 is known, u2 star is known. Of course, the cross section areas a1 a2 are known. So what you have is you get an equation u2 prime a2 equals u1 a1 minus u2 star a2, right? Of course, u1 is a given boundary condition. Okay. So let's call this equation number 10. Now what we can do is we can, of course, take the momentum interpolated phase value. In order to substitute for u2 prime, we have to go back and look at this equation 9, that is your momentum interpolated phase value, and obtain the prime equation in terms of pressure correction. So this is basically from momentum interpolated phase value, what we have is u2 equals u2 hat plus d2 times pv minus pc, right? So from here, if I subtract off this from, or if I subtract a star corresponding equation for stars from this equation, what you get is an equation for primes, right? So this minus u2 star would give me u2 prime. Similarly, on the right hand side, that's basically going to give you ut prime equals ut hat prime plus d2 times pb prime minus pc prime. Again, u2 hat prime would contain all the neighboring coefficients and everything, which will be neglected as part of the simple algorithm, right? That means u2 prime hat is 0. So what you have is u2 prime equals d2 times pv prime minus pc prime. So this is what we are going to substitute for u2 prime in equation 10. Okay. So that's going to give you essentially a2 times d2 times pb prime minus pc prime if we substitute for u2 prime in equation 10. On the right hand side we have u1 a1 minus u2 star a2. Okay. So essentially we obtained a pressure correction equation, right, for cell B, right? So this is a pressure correction equation in terms of PV prime and PC prime equals U1 A1 minus U2 star A2. Okay. So that is equation 11. Okay. So we have two pressure corrections that are unknown. We have obtained one equation. How do you get the other equation? Basically write the continuity equation for cell C, right? Because we have now written equation for, this is equation for cell B. So now write an equation for cell C. Okay. So but basically discretize the continuity equation for cell C. So that's going to give you integral 2 to 3 ddx of ua equals 0. This will give you u3 a3 minus u2 a2 equals 0. Again, u3 is given as a boundary condition. So this would be, this cannot be split into star and prime quantities, whereas u2 can be split. So this is basically minus u2 prime a2 minus u2 star a2 minus u2 prime a2 plus u3 a3 equals 0. Again, you leave out u2 prime a2 to the right hand side, then u2 prime a2 equals basically u3 a3 minus u2 star a2. Okay. Again, of course, from mass conservation, we know that u3 a3 is nothing but u1 a1. Okay. So I can write this equation as u2 prime a2 equals u1 a1 minus u2 star a2. This is exactly the same equation we have got before here in the context of cell B as well, right? u2 prime a2 equals u1 a1 minus u2 star a2. Okay, so that means we got the same equation for both the cells. Again, if you plug in for u2 prime in terms of pressure primes, what you get is a2 d2 times pb prime minus pc prime equals u1 a1 minus u2 star a2. So equation 12 for cell C is the same as equation 11. That means what we got here for cell B, right? Now, why is that? Why is the two equations the same? Why are the both equations the same? That means that we don't have any additional equation. That means that the two cells together is basically giving you only one equation. That is because basically both the boundary conditions that are given for are for velocity, right? As a result, there is no boundary condition given for pressure. Therefore, the pressure that you obtain from these calculations, P, as well as if you add any constant to that pressure, so both P and P plus C will be solutions for these equations. Okay. As a result, you cannot fix pressure level. Rather, you can only find it up to a constant, right? So pressure level cannot be fixed. Rather, you can find every pressure with in relation or with reference to one of the pressures here. So you have to you can only find pressure up to a constant, okay? Because no boundary condition for pressure is given, but that is not a problem. That is not going to make any issues, because we know that in incompressible flows, it's only the pressure gradient that matters. It's not the absolute pressure, okay? That drives the flow. Okay, as a result, we would like to fix one of the pressures. So either you can take Bp prime equals 0 or any other value, 10, 20, whatever, or Pc prime equals some constant. I would like to take Pc prime as 0. That's basically some kind of a reference value for pressure correction for cell C. Okay, we are taking. So everything will come in terms of Pc prime. Okay, all right. Now, once you get the solution, if you change Pc prime to something else, everything will get added up by that value. Okay, that means if Pc prime is 0, what you have is A2 D2 Pb prime equals U1 A1 minus U2 star A2. Okay, that means A2 D2 Pb prime equals U1 A1 minus U2 star A2. Okay, that's what we have. That means we can calculate what is the pressure correction required at the cell B as Pb prime equals basically this term divided by D2A2, okay? That is U1 A1 minus U2 star A2 upon D2 times A2. So this is the pressure correction for cell B. Once you know the velocity corrections, you can calculate this value, okay? But we also know that U2 prime, once you know the Pb prime, you can update what is the velocity correction at phase 2 as U2 prime equals D2 times Pb prime minus Pc prime, right? And once you know U2 prime, you can add it to U2 star and update your value on the phase. Okay, that can be done. And we also know that our boundary conditions are given for phases 1 and 3, right? U1 is given as some value and U3 is given as some value. As a result, there is no correction for U1 and U3. So U1 prime equals 0 and U3 prime equals 0. So if you go to equations 6 and 8, where U1 primes are related, okay, that's basically, yeah, so essentially we are talking about this one. A1 U1 equals P1 minus PB plus B1. So U1 prime equals, right, U1 prime equals, we would neglect this guy, right, because if you write, if you go back to, maybe I should look at this one, okay, this one, the corresponding equation is here. Okay, so U1 equals, yeah, so U1 prime equation for here will be U1 prime equals, this will be neglected. So as a result, what you get is P1 prime minus PB prime, right, because this is neglected in simple. So U1 prime is 0. If this is 0, P1 prime has to be equal to PB prime, right? Similarly, PC prime equals P3 prime when U3 prime is 0. Okay, so those are the two equations we have. That means if we go back to this thing, that means from these equations we can write that because U1 prime and U3 prime are 0, the pressure correction on the phase 1 is the same as the pressure correction on the neighboring cell center. Okay, so P1 prime equals PB prime. Okay, remember this is the pressure correction is the same, not the pressures. Okay, the pressures could be different. Now P3 prime equals PC prime, because this is what is coming out from applying the momentum equations to the boundary cells, and using that discretization we are able to comment on the pressure corrections on the phases. Okay, so P1 prime equals PB prime and P3 prime equals PC prime. Okay, and as usual, if you have a central difference approximation, arithmetic average, essentially you update the pressure on the phase 2 as PB prime plus PC prime by 2. Essentially we are doing all this once you solve for the pressure correction equation. Okay, so solve for pressure correction, then update your velocity corrections, also update your pressures on the phases. Okay, how do you update the pressures on the phases? You have to go back to the corresponding momentum equations that you have derived from the half cells as such. Okay, All right, then we have all these pressure corrections and everything ready. Then what we have to do is we have to kind of correct the pressures. So cell pressures are now PB equals PB star plus alpha P times PB prime. So essentially have some kind of an under relaxation for pressure, okay, and also the pressure at cell C is basically PC equals PC star plus alpha P times PC prime, okay. Then what do? You can correct the velocities at the cells, cell center velocities, that is UB prime equals dB times P1 prime minus P2 prime, UC prime equals DC times P2 prime minus P3 prime. How did these equations come by? These are again coming from the corresponding cell equations. Right now we are doing this only to increase the convergence, improve the convergence, okay. Then you can correct the velocity corrections to the start values at the cell. So these are basically the cell corrections used for improving convergence, okay. Otherwise these are not required, okay. Then one more thing that is still remaining to be done is basically you need to update the boundary pressures, okay. We have calculated what is the pressure correction on the faces, but we have not updated the pressures on the boundaries. So how do you update the pressures on the boundaries? Again from the momentum equation, if you remember, we had U1 equals U1 hat plus D1 times P1 minus PB. So that equation I am recasting it as an equation for pressure on the boundary, that is P1 equals PB plus U1 minus U1 hat by D1, okay. So everything is known on the right hand side. The boundary pressure can be updated, okay. So basically these are equations for boundary pressure update, okay. These are again coming from the momentum equations that are discretized on half cell concept, okay. Okay, then similarly we had an equation for U3 as on the right hand side boundary face, U3 equals U3 hat plus D3 times P3 minus PC or something. So from there I can write it as P3 equals PC minus U3 hat by D3, okay. So once you know the cell pressures, you know the hat velocities, you can update now the boundary pressures. Now you can see that P1 prime equals PB prime, but not P1 is not equal to PB, okay. P1 and PB are off by U1 and U1 hat, okay. Similarly, once you correct the pressures on the boundary faces, you can also correct the pressure on the interior faces. This is basically arithmetic average of PB and PC, okay. So essentially update pressure on the interior faces from the neighboring cell values using arithmetic average, okay. Alright, that finishes the algorithm. Then we can go back with the new pressures and new velocities and then continue doing this, okay. Alright, so that is about the simple algorithm on a collocated grid. Now let us look at the corresponding code. Again, I have written this in Fortran, okay. I'll go back to the front of this thing, okay. So I'll go back to the code we have, okay. This code is now again also written in Fortran. We will kind of try to understand, draw correspondence between what we have derived and this code, okay. So essentially this part is basically declaration of variables. So what we have is A1, A2, A3, these are basically your areas. Then C1, C2, all these things are delta X tolerance, these are the porosity constants and the delta X and tolerance. Then we have AB, AC, A1, A2, A3. So remember here I have capital A underscore 1, 2, 3 to define basically the cross-sectional areas, okay. Whereas these ones are AB, AC, A1, A2. These are basically the coefficients for momentum equations for cells, okay. So and then we have UB, UC, U1, U2, U3. These are UB, UC are the velocities for the cells, U1, U2, U3 are the velocities on the faces, and then we have UB prime, UC prime, U2 prime, and then we have UB hat, UC hat, and then U1 hat, U2 hat, U3 hat. These are all basically the variable declarations. Then assign given values in the problem statement. So the cross-section area is given as 642 for at locations faces 1, 2, 3, and U1 is given and as 10, U3 is given as 30. These are basically the boundary conditions for velocities. Then delta X equals 2, Then of course the porosity constant C1, everything I'm taking it as 10. You are welcome to take any other values here in a particular problem. Then we need to start off with an initial guess. The initial guess for the cell centroids, we are taking it as 15 for both UB and UC, and the pressure we are taking it as a initial guess for pressure at all the cell centers as well as on the faces. We are taking it as 120. Okay. And of course, let us set the tolerance value, that is come out of this loop if your sum of your U residual and momentum residual and the continuity residual is falls below 1 minus 6. So that's what it is. And then we also set some under relaxation parameters, alpha p and alpha u. These are under relaxation for pressure and velocity. And let us hope that we don't hit 200 iterations in this loop, and we try to converge much before that. Okay. So again, we have to fix BC prime because both the boundary conditions are given for velocities only, right? So as a result, we fix BC prime, and then let us initialize the residual values of U residual and C residual to some arbitrary values. Okay. Then we have some print statement to print all the, as we progress, we want to print the iteration. UB, UC, the velocities and the pressures at the cells, and we also want to print the momentum residual and the continuity residual. Okay, so this is the main iteration loop. Do I equals 1 to I max. This is like your for loop. Then compute and update coefficients for momentum equation. So what is your AB? AB equals CB mod UB, CB mod UB delta X times divided by alpha U, right? Do you remember this thing? So this is basically AB, right? AB is CB mod UB delta X. That's your CB mod UB delta X divided by alpha U. This is basically divided by alpha U. Okay. So that's your AB. Then your BB would be 1 minus alpha U by alpha U. That is why alpha U is already in here in AB. So I don't have to write that. This is basically 1 minus alpha U times AB times UB star. Okay. That's your BB value. Similarly, AC equals CC mod UC delta X by alpha U, and BC would equal to 1 minus alpha U by alpha U times AC, but AC is already divided with alpha U, so we don't have to write that, and we have AC UC star. Okay. These are your AC and BC values and AB and BB values that we have here. Okay. So this is your BC and AC. These are populated. Then similar to what we have for the cells, we also have these boundary coefficients, that is basically A1 equals C1 mod U1 delta X by 2. Remember, we had a 2 in here, right? So we had a 2 in here. Similarly, B1 would be equal to 1 minus alpha U times A1 times U1 star, right? 1 minus alpha U by alpha U, that is here. Okay. Similarly, A3 would be equal to C3 mod U3 delta X by 2, and then divide by alpha U. And your B3 would be equal to 1 minus alpha U by alpha U times A3 U3 star. Okay. But A3 already got the division, so we don't have to again write it. So these are basically your this equation, okay, and this equation. Okay. Basically these equations are written here. So this basically completes the momentum equations for the cells B and C as well as the boundary cells also. Right. Okay, now we calculate what is the momentum residual. Momentum residual is nothing but take everything to the left hand side, that is basically ABUB minus P1 minus P2 minus BB. That's basically, if you go here, we don't have the equation here. Okay, so this is your momentum equation taken to the left hand side. Okay, similarly this is your momentum equation taken to the left hand side for cell C, that is ACUC minus P2 minus P3 minus BC. All right. Then I want to normalize this thing. So basically this is your residual calculation from the momentum equations. Okay, these are the momentum equations. They are right here. So from here you can construct what these quantities are, right? What this quantity is basically this equation, everything taken to left hand side. Okay. Then you solve for the momentum equations at cells B and C. So UB equals P1 minus P2 plus BB upon AB. Similarly, UC equals P2 minus P3 plus BC upon AC. These equations already have under relaxation in them, right? Because we have already divided with alpha U's up here. Okay. So these equations already have incorporated under relaxation in them because AB, AC, BB, BC already contain those things. Right. So once you have UB and UC, now it's time to update the hat velocities. How do you calculate UB hat? UB hat is your BB upon AB, right? Essentially, that is this guy divided by AB, right? And similarly, UC hat is BC by AC. This is what we have written here, right? UB hat is BB by AB, DB is 1 by AB, similarly UC hat is BC by AC. So I update what is UB hat, UC hat, then U2 hat you will find it as arithmetic average of UB and UC hats. Then your U1 hat would be B1 by A1, U3 hat would be B3 by A3, right? So that's what we have here, right? Basically U3 by, right, you have B3 by A3 is U3 hat, okay. Then we can also write the coefficients D that multiply the pressure difference. So dB equals 1 by AB, DC equals 1 by AC, D2 equals dB plus DC by 2, excuse me. And then this is basically coming from momentum interpolation. Then D1 equals 1 by A1, D3 equals 1 by A3, okay. All right, then use momentum interpolation and calculate the star velocity, right? Phase velocity, phase star velocity. So U2 equals U2 hat plus D2 times PB minus PC, right? That's your momentum interpolated value. U2 equals U2 hat plus D2 times PB minus PC. Because we have already calculated what is U2 hat, what is D2, we can do this thing, right? Use momentum interpolation. Then here I am checking for convergence. If my continuity and momentum residuals together are less than the tolerance, then I would print off several values. All right, then once you have the momentum interpolated phase values, we can go and solve for the pressure correction equation. So this is the pressure correction equation, that is PB prime equals U1 A1 minus U2 star A2 divided by D2 A2, right? That's your pressure correction equation. If you remember, we set PC prime equal to already 0, right, which gave us this equation, right? This is PB prime equals U1 A1 minus U2 star A2 by D2 A2, okay? So that's the equation here. Then once you solve for pressure at the cells, pressure correction at the cells, you can update the boundary pressure correction. So what we have is P1 prime equals PB prime, that's coming from here, and P3 prime equals PC prime, that's coming from here, right? Okay, and then P2 prime equals arithmetic average of the neighboring cell values, that is written here, okay? So we have, these are the pressure corrections. First two are written from the boundary cell momentum equations, right, which relate the pressure to the boundary velocities. All right, so once you have all the pressures, the cell pressures and the phase pressures, then you can correct the phase velocities by computing the phase velocity corrections, okay. So U2 prime equals, this is again D2 times PB prime minus PC prime. This is coming from where? This is coming from momentum interpolation, right? Okay, then U2 equals U2 plus U2 star plus U2 prime. Then your PC, the cell pressure, equals PC plus alpha P times PC prime. That's basically pressure correction. So that is these equations, PC and PB equals PB plus alpha P times PB prime. Then you can correct the velocities, cell velocities, as UB equals UB plus dB times P1 prime minus P2 prime, because P1 prime, P2 prime are already corrected, updated here, so that can be used and correct the cell values. This we are doing essentially primarily this is basically to improve convergence, right? Okay, that's what we have written here. We're doing this thing, okay, you calculate UB prime and add to the UB star values. All right, then update the phase pressures, okay, that's basically the final step here, right? Update the phase pressures because only the phase velocities are given. So update the phase pressures from the U1 and U3 equations, right? The phase values of the pressure. So this will be P1 equals PB plus U1 minus U1 hat by D1. P3 equals PC minus U3 hat by D3. That's written here, okay. And then P2 would be arithmetic average of the cell values, okay, that's written here. All right, that means again, that means we are done with all the corrections, right? These are the phase pressure updates. Okay, then calculate the continuity residual. C residual equals essentially U1A1 minus U2A2. Of course, you can even add the other component, that is this is for cell B. You can also add the other component that is coming from cell C as well, okay, and then normalize with the continuity value, okay. and essentially write down all this information. Okay, fine. We can also do the continuity residual as absolute plus absolute of u2 star a2 minus u3 star a3, right? That would be the total value for both the cells, and of course it can be also divided. Okay, so this is the complete program. So let's try to compile and run it. This is gfortran simple porous, collocated porous. So /a.out. Okay, that's good. So the program ran. Now what we are looking at here is basically the iteration count, UB value, UC value, pressure at B and C, and the U residual and the continuity residual. As you can see, continuity residual is always 0, as it should be, because simple algorithm makes sure that the velocities satisfy continuity after the correction. Okay, whereas the momentum residual, you can see that it slightly increases and then it starts to decrease all the way to 1e minus 6, and because PC prime was set equal to 0, so PC remained at its fixed value of 120. That was the initial guess, and PB of course changed, and the solution converged in 29 iterations, and UB and UC values converged to 13 and 23. Okay, so the converged values of UB is 13, UC is 23, and the cell pressures are 4880, that is 5000. Cell pressure PC was set to 120, and P1 is basically the phase pressure, that is around 5900. So you can see there is a difference between P1 and PB, right? Because this is because of the porosity, right? This pressure difference should be there so that the flow can accelerate while it is going through the porous media, right? Similarly, we have P3 equals minus 8880. So basically this can be thought of as this is coming out to minus because we have fixed this to be 120, right? Otherwise, if you make this as 0, everything will get increased, get added up correspondingly. Okay, so that is the converged pressure and velocity fields. These of course satisfy the momentum equation and the continuity equations to this precision. Okay, I mean, we can also see how you can also change any of these coefficients and play with them as well. You can change essentially the porosity constants or the cross-section areas and things like that, as long as the problem is well posed. Okay, fine. So that is an example on how would you go about solving simple algorithm on a collocated grid. Okay, so this kind of collocated algorithms are only used in the regular software when you try to solve incompressible flows. Okay, so that is kind of good to know. Okay, so I will share this program so you can kind of go through it, and if you have any questions you can get back to me. So I'm going to stop here for today. We will catch up in the next class. If you have any questions, do send me an email. Okay, thank you.